Have you ever really stopped to think about how a machine sees? I mean, it's happening all around us, right? Inside your phone's camera, in the self-driving cars on the news, even in the scanners the doctors use. So today we're going to dive into that. We're going to break down the very first, most fundamental step in teaching a computer to make sense of our visual world.
So yeah, let's just start right there with that big question. When you look at a picture, your brain just gets it, right? You see friends, a landscape, a cat, whatever. It's instant. But what about a computer? How does it even begin to process that same image? How does it go from just a bunch of pixels to actually understanding what's inside the picture?
All right, let's really get into the weeds here. To you and me, this is obviously a picture of some coins. No big deal. Our brains just see objects. But for a computer, it sees something totally different. It sees a giant grid of numbers. That's it. Each number just represents how bright a single dot, a pixel, is. It's just a sea of data, pure digital chaos with zero meaning. So the first huge challenge is, how do you turn that chaos into some kind of order?
Okay, so to figure that out, here's what we're going to cover. First, we'll define what image segmentation even is. Then, we'll look at how a computer finds the absolute simplest features. After that, we'll get into the real art of edge detection, deal with a tricky problem called visual noise, and finally, we'll wrap it all up by talking about why this stuff actually matters so much.
All right, let's jump right into part one. What exactly is image segmentation?
You know, the simplest way to think about it is that image segmentation is basically the process of teaching a computer to draw outlines. It's all about taking that big mess of pixels and sorting them into groups that actually line up with real-world objects. And this isn't just some optional step. It is the absolute bedrock, the first thing you have to do for pretty much any kind of automated computer vision.
And check this out. This is a perfect example. On the left, you've got the raw image. Honestly, it's kind of hard to tell what's going on, even for us. It's just a blurry blob. But look at the right. After segmentation, the computer has sorted all those pixels and slapped a boundary around each object. Boom! It's order from chaos, right there. That's exactly what we're trying to do. So how does a computer even start to do this? Well, you can think of it like a little kid learning to draw. You don't start with a complex portrait, right? You start with the absolute basics, the simplest features you can find.
The fancy term for what it's looking for is discontinuities. But all that really means is it's scanning for sudden, abrupt changes in brightness, and it learns to spot three basic things, kind of building up in complexity. It starts with simple, isolated points, then it moves on to straight lines, and finally, it gets to the big one, edges.
Now, the way it finds these things is pretty cool. It uses a tool called a mask. Just think of it like a tiny digital magnifying glass. This little grid of numbers slides across the entire image, one pixel at a time, and the numbers inside the mask are set up in a very specific way, so that it only lights up, gives a strong response when it lands right on top of a single bright spot surrounded by darkness. And this isn't just theoretical stuff, it's incredibly powerful in the real world. So on the left here, you're looking at an X-ray of a turbine blade. To you or me, it probably looks okay, but the computer slides that point detection mask over it and bam, look at the right. A single, solitary bright dot pops out. That's a tiny, critical flaw that the machine found all by itself.
And the whole process just builds from there. Once the computer knows how to find a point, it can learn to find a line. It's the same exact idea. It uses these masks, but you can see their shape differently. Each one has a pattern of numbers that's tuned to look for one specific thing. One mask looks for horizontal lines, another for vertical, and yep, you guessed it, others for diagonal lines.
So points and lines are great, but that leads us to the most important part of this whole thing. Because finding the complete boundary of an object, well, that requires what you might call the art of edge detection. Now, in some perfect imaginary world, an edge would be what we call an ideal edge. It would be a sheer cliff, an instant jump from dark to light. But that's not how real life works, is it? Because of things like camera lenses, lighting, and just plain physics, real edges are almost always a little blurry. They're less like a cliff and more like a gentle ramp. And the big challenge is figuring out where the exact middle of that blurry ramp is.
So how on earth does a computer find the exact center of that blurry ramp? Well, it uses a concept from calculus called a derivative. But don't worry, you don't need to remember any high school math. The idea is actually pretty intuitive. The first derivative is like a little alarm that goes off at the start of the ramp and the end of the ramp. It tells you an edge is nearby. But the second derivative is the real MVP. It finds the single steepest point of that ramp, its center line, and basically shouts, the edge is right here.
And how does it do that calculation?
You guessed it, we're back to our trusty masks. Some of the most popular methods, like the Pruitt and Sobel operators, use special masks that are built to calculate something called the image gradient. And all that is a fancy way of measuring how steep that brightness ramp is and which direction it's pointing.
And here's what that looks like in the real world. It's awesome. You start with the original photo of the building. Then the algorithm goes to work, sliding those Sobel masks across the whole thing, looking for every important edge. And the result is what you see here. It's what the computer sees, a perfect clean line drawing that captures the entire structure of the building. What a transformation, right?
But, it's never quite that easy. Real-world pictures are often messy, they're not perfect. And this brings up a huge problem that every engineer in this field has to deal with: visual noise. So here's the catch, the big but. Those derivative-based methods we just talked about, the very things that are so amazing at finding edges, well, they have a weakness. They are extremely sensitive to any kind of random speckle or imperfection in an image, what we call noise. And this visualizes the problem perfectly. Up top, you have that nice, smooth, clean ramp. An algorithm can handle that, no problem. But look at the bottom. That's the exact same edge, but with a little random noise thrown in. It becomes this jagged, chaotic mess. And when you try to find the steepest point of that, the calculations just go completely haywire. So what do? Well, the solution is actually pretty logical when you think about it. You just have to do it in 2 steps. First, you smooth the image out to get rid of all that noise, kind of like sanding a rough piece of wood. And then, once you have a nice, clean image, you run your edge detector. And this leads to one of the most elegant solutions in all of computer vision. It's called the Laplacian of Gaussian operator, which is a mouthful, so everybody just calls it the Mexican hat filter. Because, well, look at it. And what's so brilliant about this thing is that it does both of those steps, the smoothing and the edge finding, all in one go. It's a single, super efficient operation that saves a ton of processing time.
Okay, so we've gotten pretty deep into the how of all this. But let's pull back for a second and talk about the why. Because this is so much more than just a cool programming trick. Why does finding edges matter so much in the real world?
Well, the truth is, this one fundamental skill, finding the edges of things, is the engine driving countless technologies we use every day. Think about it. A self-driving car seeing a pedestrian. That starts with edge detection. Your phone using your face to unlock. It's finding the edges of your features. Quality control on a factory line, medical software that helps doctors spot tumors in an MRI. The list goes on and on. It all comes back to this one basic idea. So when you boil it all down, we've managed to teach machines the very first critical part of seeing: how to find the outlines of the world, how to separate one thing from another. It's a pretty incredible achievement, really. And it leaves us with a really exciting question to chew on. Now that computers can find the edges of objects, what are they going to learn to see next?